do some more and different kinds of buoyancy problems. We were here, I think this is page 193. I want to give you a different kind of problem. Let's say that we have, we'll work one. You'll see one like this in the old test in just a bit. But let's say that we have a wooden raft that floats partially submerged. And I'll tell you that the density of wood is equal to 600 kilograms per cubic meter. The area of the top of the raft is equal to 5.7 square meters. So if I'm looking at my raft, this is sort of an outline of it. The area is just this top part. And the volume of the raft, the total volume of the raft, is 0.6 cubic meters. So that includes the entire raft. And this thing is floating, it's just partially submerged. So the level of the water, as this thing sits in the water, is not completely submerged, it's just partially submerged. And I want to know what part of it is submerged. That is, what is the distance that this thing is submerged? Where is its water line? You know what a water line is on a boat? The water line is where the water comes up to on a boat. So I want to know, where is the water line on this raft? And that's it. Yeah, so what is H? All right. So there are a couple of things we'll need to think about. First of all, we want to think about what are the forces that are involved. There are two forces that are acting on this raft. What are they? Two forces. They're both acting in the y direction. Weight is one of them, and the buoyant force. And because this thing is not zooming up or zooming down, it has zero acceleration, then I know that the sum of those forces has to equal 0. So I could say the sum of the forces in the y direction, that's the force buoyant, which is up, Fb is up, minus the weight, which is down, Fw is down, that has to equal to 0. So the buoyant force has to equal the weight of this raft. All right. Further, I know that the buoyant force is equal to the density of the fluid times the volume of the object, although in this case it's not the full volume of the object because only part of it is submerged. So I'm going to put another little descriptor there that this is the density of the fluid times the volume of the object submerged. So some fraction of that volume is submerged times G. And then that's equal to the mass of the raft times G. Our G's cancel, so I'll just get rid of those. My first step here, I eventually want to know what is this height, but if I can find the volume, then I can step back and I can figure out what the height is. And I'll show you how that is in just a second. But I know the density of the fluid. What is the density of the fluid? Okay, it's 1,000 actually. It's 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. Listen, a common mistake that students make on these problems is they'll take a density that's given in the problem and they'll sort of run with it. So often students would say, well, the density of the fluid is 600 kilograms per cubic meter. But that's not what it is. That's the density of the solid, which is what the raft is made out of. In this case, we're floating in water, and the density of the fluid is 1,000 kilograms per cubic meter. So I have 1,000 times the volume, and then that's equal to the mass of the raft. I don't know the mass of the raft right off, but I can find it, right? How can I find the mass of our raft? Well, I know the density of the raft, and I know the volume of the raft, right? So my mass then is density times volume. All right, so that's going to be 600 times 0.6 which is 360 kilograms. So this is equal to 360 kilograms. And then I can find the volume that is submerged, which is going to be, I don't have that. The submerged volume is, it's 360 over 1,000, so it's 0.36 cubic meters. And then from there we need to find out what is the height. Now, how do I find the height? This will come up in some of your problems, and you'll probably see this come up on your test as well. But how do I find the height? Now, I know the volume that is submerged. I know that this volume is this little piece, the bottom part of the raft. It's 0.6 cubic, or not 0.6, whatever, 0.36 cubic meters. So a little more than half of the raft is submerged. But now I want to figure out what is the height. Now, if I have a three-dimensional object, this came up recently when we were deriving the pressure of a fluid. If I have a three-dimensional object, the volume is equal to the area times the height. In general, this is true. If it's a cylinder, for example, the area of the cylinder times the height of the cylinder, that's equal to the volume. If it's a rectangular prism, which is what we have here, I take the area of a face and I multiply it through by the height. In general, this is always true for three-dimensional objects that are regular, that it's the area of a face times the height. And since I know the area of a face and I know the volume, I can figure out the height. So I say 0.36 cubic meters. We gave you the area is 5.7 meters squared times the height, and then we solved that for h, which is 0.36 over 5.7. And I get 0.063 meters. That's 6.3 centimeters. That's how much of it, about this much of our raft is submerged. A wooden raft, again, about a little more than half of it is submerged in the water. All right, let's try a similar question on your own. Can I go away from here? Maybe just a second more. Okay, we're going to go to the back of the book. There's a question. Yeah, here it is, number 11. I think this is exam 4. It says a rectangular boat is 2 by 2 meter by 1 meter. So what depth is the boat submerged if it has a mass of 500 kilograms? So you're going to start with our buoyant force is equal to our weight. And then you'll go from there. And you want to figure out what is the depth, or what we call it H in the previous problem. What is the depth that this boat is submerged? This is number 11. It is exam 4, right? I'll do that. I'll be right back. All right, doing pretty well so far, those of you that clicked in. All right, we'll stop at 220, 220, 220. Just 5 more seconds. Guess if you're not sure. All right. Okay, good. C is right. So I start with the idea that my buoyant force is equal to my weight. And if it's not, if there are no other forces involved and it's just floating, then that's always going to be true, that our buoyant force is equal to the weight. And our buoyant force is equal to the density of the fluid times the volume of the object that is submerged times G, and then that's equal to M times G. My G's cancel. Let's go ahead and solve for the volume of the object. That's going to be equal to the mass of the object times the density of the fluid. It's important to keep all your subscripts here because you got different densities floating around. Ha ha ha. Okay, so you need to make sure you keep your proper subscripts. That's going to be 500 over 1,000, which is the density of water, or 0.5 cubic meters. And then we go to this idea that volume is equal to area times height, which the area is 2 times 1, because it's 2 meter by 1 meter, times the height, which is equal to 0.5, and so the height is 0.5 divided by 2, which is C. All right, 90%, that's good. So what do you call a snarky criminal that is going downstairs? What do you call a snarky criminal going downstairs? Oh, you heard this. You can't hear you. A condescending. Okay. While we're here, let's go ahead and try number 12. I'll blow it up a little bit. A boat carrying a large chunk of steel is floating on a lake. The chunk is then thrown overboard and sinks. What happens to the water level in the lake? So what happens is, you have a lake, you have a boat in the lake, the boat is holding a piece of steel. You take that steel and you throw it out of the boat and into the lake. What's going to happen to the water level in the lake? Is it going to go up? Will it rise with respect to the shore? Will the water level drop with respect to the shore? Will it remain the same, or does it depend on the mass of the steel? What you want to think about is, when does the steel displace more water? Does it displace more water when it's in the boat? Or does it displace more water when it's sitting on the bottom of the lake? And when it displaces more water, what's that going to cause the level of the lake to do? If it displaces a lot of water, does that mean the level of the lake will go up or come down? Okay, we'll stop at 130. 130? I'll go on to 135. Let's go ahead and guess if you're not sure. 135? Okay, the water level, when you throw it into the lake, is going to drop. Because when the steel is in the boat, it displaces the volume of water that's equal to its weight. That's Archimedes' principle. That the buoyant force, which when it's in the boat is equal to the weight of the steel, is equal to the weight of the displaced fluid. So when the steel is in the boat, it displaces the volume of water that's equal to its weight. Now, is steel more or less dense than water? It's more dense than water. That's why it sinks when you put it in the water. And so, if you have a piece of steel, and then you have some water that's equal to it in weight, which is going to be bigger, the steel or the water? The water will be quite a bit bigger because it's less dense than steel. So the mass of water that's equal to the mass of the steel will have a bigger volume, more water, less steel. That's when it's in the boat. But when you throw it out of the boat, it only takes up its own volume in the lake. That's how much volume it displaces. So when you have it out of the boat, you throw it into the lake, it doesn't displace nearly as much water as when it's in the boat. All right, I want to show you something that's kind of cool. We'll go back to let's try this quick test, then I'll show you this thing. This is back on the page where we were before. I'm going to have to throw away your flower because it's all nasty.
Yeah, and water.
Mass, a block has a mass of 1 kilogram and puts halfway submerged. What is the density of the object? You might be able to reason what the density is just by thinking about how should the density of the object compare to the density of the water. You can work through it, and that's okay. But you might be able to reason it out, too. All right, we'll stop at 145, 145. Okay, good. D is right. Like I said, you can probably reason out that the density of this object, which is floating just halfway submerged, is going to be half as dense as the fluid. But we can think about it here. I have this block, and it sits halfway submerged, and I want to know the density of the object. I can start with this, that the buoyant force is equal to the weight of the object. The buoyant force is the density of the fluid, the volume of the object, and this is submerged times G, and then this is equal to M times G. We can say that the density of the fluid, this is equal to the volume of the object divided by 2, because only half of the object is floating or is submerged, times G. This is equal to M times G, and then my G's cancel, and I can say that the density of the fluid is equal to, divided by 2, is equal to the mass over the volume of the object. And this mass over the volume of the object, this is the density of the object, and it's equal to 1/2 the density of the fluid. So this follows from our Archimedes principle. Again, starting, the buoyant force is equal to the weight. The buoyant force is this, rho VG equal to m times g. My g's cancel. And then you realize that only half of my object is submerged, so that's where this over 2 comes from. And then I solve for the mass of the object over the volume of the object, which is the density of the object, which is 1/2 the density of the fluid. All right, we're not going to do the next question. It's just not a very good question. Yeah.
I don't understand how you did that.
Okay. When I solve this, I divide both sides by volume of the object, and I'm left with the density of the fluid divided by 2 equals this divided by this. I just divide through both sides by the volume of the object, and that cancels this out and moves it over here. Let me write it on here. So both sides, I do 1 over the volume of the object. Then this cancels here and here, and I'm left with this density of the fluid over 2. So I get rho divided by 2 equals m over v of the object. Does that help? Oh yeah, you can do that. You can, in fact, some people like to write things like this. You would just say rho vg, all of that divided by 2. That's okay. All right? Is that clear? All right, awesome. Okay, let me show you something. Can I pour that in there? Yeah. Do y'all know what the density of peanuts is? Do you think that peanuts are more or less dense than water? You think they're less dense? So if I put peanuts in the water, what will they do if they're less dense? They'll do what? They'll float, right? So let's see. So I'm going to have this is plain water. This water. I'm going to put the peanuts in there. And what do they do? Y'all see? Some. So the density of peanuts is bigger or smaller than the density of water? Bigger, right? They're slightly bigger, but slightly higher density than the density of water. Now I'm going to do something. Your dads ever drink, like put peanuts in their Coke? That's not what I said. Did your dads ever put peanuts in their Coke? I don't think people do it as much anymore. Yeah, I think it's a generation gap. All right, look. What happens when you put peanuts in your Coke? It's not even funny. Okay, you ready? So what I'm going to do, I have a club soda. It's just, carbonated water. I'm going to pour it in here. So about a 2 to 1. Get some peanuts. I'll come back here. Can y'all see it? I stand in the middle. No. Right, so now I'm going to drop some peanuts down in here. Peanuts are slightly more dense than water, so they drop down to the bottom. Oh. Well, look, you see what's happening? It's like a peanut bottleneck. Now there's one more down there. Little fella. Oh, you see? You know what they're doing? They're floating. Why are they floating? What about the carbonation? Do you think that the carbonated water is less dense than water? If it was less dense than water, then the buoyant force would be what? More or less? It would be less, right? So that's not it. The carbonated water isn't less dense. What are you saying? It's actually, I think it's right at the same density, right? It just has carbon dioxide in solution. But it's like the peanuts, y'all can't see them, but it's like they're wearing little ice preservers. They have little bubbles all over them. So when they go into the carbonated water, they get all these bubbles that stick to them because of the salt on the peanuts, and it draws that carbon dioxide out of them. And that increases their total volume, but it doesn't increase their mass. And when it increases their volume, that gives them a bigger buoyant force. Because their buoyant force is rho vg. If you increase v, then that increases your buoyant force. Okay. All right. Let's move on to fluid flow. We're gonna skip this quick test. It's just it's not a good question at all. It's just not correct. Okay, so we're gonna look at the motion of an ideal fluid, and we'll have a couple things that we'll look at here. You've probably never seen this. You might have, possibly, but probably not. The equation of continuity we'll see, and we'll also see Bernoulli's principle. I think that's all that we're gonna see. Yeah. But first of all, when we're looking at an ideal fluid, there are some properties that we'll need to assume for our fluid. First of all, that it's non-viscous. That means that we have negligible friction. Between the molecules. That means that the molecules can just move around one another very easily. So for example, water is relatively non-viscous. The molecules of water can move apart from one another very easily. But on the other hand, I don't know, maple syrup is fairly viscous. That's why it flows more slowly. It needs to be incompressible. That means that the density is constant. Regardless of the pressure. Most liquids are incompressible. So when we're talking about fluid flow, that will completely exclude all gases, because gases are not incompressible. No, there is no gas that is incompressible, and almost all liquids are incompressible. Remember, this came up with Pascal's principle. Pascal's principle said if you apply a certain pressure at a liquid, it'll feel that way all throughout that liquid, and that's how we have hydraulic lifts. But you know that in a hydraulic lift, you have hydraulic fluid, which is an oil. You don't have to use oil in a hydraulic lift. You could use water. You could use any kind of liquid that you want. Why do we not use water in a hydraulic lift? It would do what? No, it doesn't have to do with the density. Hydraulic oil is more dense than water, but that's not it. Yeah, Tyler? No, it wouldn't be the friction and heat necessarily. Although it does have less friction, you're right. But primarily what? Rust. It would rust, right. So when you put water in metal pieces, they just rust. And the hydraulic fluid keeps it from doing that. All right, so steady motion. That means that the velocity, pressure, and density of a fluid do not change with time at a particular point. All right, so at a particular point, the velocity, the pressure, and the density will always be the same. And then also irrotational. That means that there's no circular motion. All right, so for example, water flowing through a pipe is ideal because it's not twirling around. And you know, water, like, I don't know, in your what? In your bathtub or in your sink or in your toilet. Your toilet swirls. Nobody wanted to say it, and I didn't want to say it either, but in your toilet it swirls, good circular motion. And so that's not ideal fluid flow. Just know these four things. You might have a question just asking you, which of these is ideal fluid flow, is required for ideal fluid flow, and I'll give you several options. And you have to pick out what is or what isn't. All right, and then we have two equations that govern the motion of an ideal fluid. The first is the equation of continuity. The equation of continuity let's say that I have a pipe that changes shape. I have an area over here, I'll call it A1. I have an area over here, I'll call it A2. These are in units of square meters or square centimeters or whatever. And then I have a speed over here, I'll call it V1. And the equation of continuity, which is based on the law of conservation of matter, we didn't really talk about this semester, but you've probably heard this in, I don't know, third grade or whatever, that matter can't be destroyed, that it can change phases and change states, but you can't destroy matter. You can't just make it not be there anymore. And so what this is saying is that if I have a certain volume of fluid flowing through this pipe at this point, I have to have the same volume of fluid flowing through this pipe. So it's basically saying that the volume flow rate is constant. And if I think of the volume flow rate, volume over time, volume is area times distance divided by time. And if you think about this distance over time, then my volume flow rate is equal to area times speed. And so the equation of continuity says that V1 times A1 is equal to V2 times A2. I'm sorry, I think I usually write it the other way. A1 V1 is A2 V2, and that's how it is on your equation sheet. But this comes about from our volume flow rate. Be careful here. This is a capital V for volume. This is a script V for speed. So this V1 and V2 represent the speed of the fluid in the pipe. Now what's going to happen when this pipe gets big to small, when it goes from big to small? With the fluid here, will it flow faster, slower, or the same speed as what it was here? Faster, slower, or the same speed here? It's going to go faster, because when A2 decreases, that means V2 has to increase in order to keep our volume flow rate constant. Our volume flow rate is always constant, because I can't just lose stuff in the pipe. So if the area goes down, the speed goes up. So if you decrease the cross-sectional area, the velocity must increase. And this happens when you squeeze the end of a garden hose. You ever do this? Or you put your thumb over the end of a garden hose? Does the water come out of the end of the garden hose faster, or does it come out slower? It comes out quite a bit faster, right? Because you're decreasing that cross-sectional area, and that causes the speed to increase. If you decrease the area, that causes the speed to increase. So when you put your thumb over the end of your garden hose, it causes your speed to increase. Now the second thing that we'll see in this chapter is Bernoulli's equation, and this is based on the conservation of energy. Sometimes I do ask questions about, like, on which law is the continuity equation based on? And you would say the law of conservation of matter. On which law is Bernoulli's principle depend upon? And that's the law of conservation of energy. It says basically that the energy per unit volume is constant. That at any point in a fluid, in a liquid in this case, because it's an ideal fluid, the energy per unit volume has to be a constant. And our energy can have three different components. Our energy can have kinetic energy, it can have gravitational potential energy, and we can do work, because a fluid can do work. That this has to be constant when they're all divided by volume. So again, be careful. My capital V is volume. Whenever I use speed, I'll do a little script V. Okay? This is the energy per unit volume. Now remember, kinetic energy is 1/2 mv squared. It's divided by volume. plus mgh divided by volume plus force times displacement divided by volume. That's all equal to a constant. And this gives us our Bernoulli's equation, because notice here that m over v, gosh, what is m over v? We've seen that before. The mass over volume is density. So I'm going to write it now instead as 1/2 rho v squared plus rho gh. And here we have to do a little bit of hand waving, but if I do distance over volume, length over volume, that's going to give me 1 over area. And so force, think, that's a thought bubble. This is the same as force over area. And force over area is, well, we've seen force over area. That is what? No, it's not work. Force per unit area, like PSI, pounds per square inch, for example. It's pressure, right. So that's going to be pressure. And I'll do a capital P for that. This, in a system, is always constant. Now usually, almost always, you have some homework questions, and as you look back in the old test, you'll see cases where the pipe actually does change height. But usually in systems, the height remains constant. And so we don't even worry about this term some of the time, most of the time, if our pipe actually stays the same height. So for example, up here, this is my height, h, and h1 is equal to h2. But what we would say on this is that since h1 is equal to h2, I can just sort of disregard this. And I would say that in this left-hand section of the pipe, that 1/2 rho 1 v1 squared plus rho gh, or excuse me, plus the pressure 1 is equal to, in the second part of the pipe, 1/2 rho v2 squared plus p2. You'll notice what I did, that I just got rid of that rho gh because h1 is equal to h2, and I subtract them from both sides. Follow me on that? Not sort of, kind of, not really. Well, let's go ahead and put them in, and I'll show you how they cancel out. Plus rho gh2. I'll put it over here, rho gh1. But since h1 is equal to h2, then I just cancel, I subtract both of these from either side. So what I have here is the energy per unit volume for a point here. And then I also have energy per unit volume for a point right here. And Bernoulli's principle says that the energy per unit volume here has to equal the energy per unit volume here, based on the conservation of energy, that our our liquid can't lose energy. Now, the result of this is that if our speed goes up, what happens to our pressure? So for example, in your garden hose, when you put your finger over the end of the garden hose and it comes out at a higher speed, what happens to the pressure? Does the pressure go up? Does the pressure go down? Or does it stay the same? You think it increases, right? Like, that makes intuitive sense. It seems like it increases. It actually decreases. The pressure, when it comes out, actually decreases because, if I look at Bernoulli's principle, if V goes up, if this side has to stay constant, if this value increases, this value has to decrease. So one of the nice features of Bernoulli's principle is that if V increases, P decreases. And similarly, if V decreases, P increases. That has lots of great applications, that if I increase the speed of my fluid, then it will decrease the pressure. One of the big ones is an airplane wing. We have an airplane wing, looks like this. You ever fly in an airplane and you look out and you think, gosh, this huge thing is going to get lifted up into the air? Does that ever just like blow your mind? Because there are some massive forces that are at work to lift that huge airplane and all the people inside and all the luggage up into the air thousands of feet. But what happens is you get air that flows over the wing and under the wing. Now at this point, your air is traveling along together. And when it breaks up here, it's gonna, whatever particles that come apart here, they're gonna come back together over at this side. So my particles that are split apart here in my airstream are gonna come back over here. Because otherwise you're gonna make a vacuum, and nature doesn't like a vacuum and all that business. So which one is gonna have the higher speed? Is the top of the wing gonna have a higher speed, or the bottom of the wing have a higher speed? Which one? They both travel the same amount of time to get around the wing. Which one is traveling the longer distance? The top. So which one travels a faster speed? The top. Because it covers a longer distance in the same amount of time. I know the bottom seems like the obvious choice, but it's not true because they cover it in the same amount of time. You cover a longer distance in that time, and so we'll have a higher speed on the top. So if I have a high speed, is my pressure big or small up here? Small. Low pressure, high pressure. So I have up top, I have a high speed and a low pressure. Down bottom, I have a low speed and a high pressure. When I get this difference in pressure, high pressure, low pressure, that's what produces lift. And that's what lifts that huge airplane up into the sky. So I get a net force that acts upwards. All right? You ever thought what happens to the pressure in an artery when I get a bunch of buildup here? What happens to the pressure in that artery? Does it increase or decrease or stay the same? Let's do it as a quick question, okay? So does the pressure in the artery right here, does the pressure A increase, B decrease, or does it C stay the same? All right, what happens to the pressure here? What happens to the pressure in this artery when you get built up right here? All right, we'll stop at 40. Stop at 40. Okay, good. B is right. I know you think when I get plaque in my arteries, that causes high blood pressure, and that is true, but that's a systemic pressure. What we have here, though, is that and there's something else going on, the Poisson equation that we're not going to get to, but if I have a block here, that means that my speed is going to increase or decrease by the equation of continuity. My speed through this block portion is going to increase. And just like the garden hose, if my speed increases, the pressure has to decrease. And so I can get a low pressure here. I will get a lower pressure here. Low pressure because the speed has increased. Remember, the speed goes up, the pressure goes down. This can cause various things. I think they call it arterial collapse, where if you get enough of a low pressure here, the whole thing will just collapse down on itself because the pressure outside the artery becomes too great and it just causes the whole thing to collapse, and then it just doesn't work anymore. But y'all probably know more about that than I do. Alrighty, let's see, I brought my hairdryer today. Because you can do this and show your friends. Now, does the hairdryer have a high or low speed in the hair? Got a high or low speed? It's faster than the air around it, right? So am I going to get a high or a low pressure here in the middle of my hair dryer? The stream coming out. Low pressure, right? So I get a low pressure here, and it's surrounded by relatively high pressure. And so I get this little column of low pressure surrounded by high pressure. So watch this. That's how it's working. So I can suspend this ping pong ball, and it's kind of stable. Actually, I can tilt it off to the side, either side, because it has this column of low pressure that sort of gives it a little tunnel to move up and down in, and then you have these high pressures on either side that will keep it in that column. If you put it on high, it doesn't work as well. Let's try. It's a little less stable.
Keep it in the column.
Yeah, it's just less stable with a high pressure. All right. Let's do it. I'll let you look. This is another one. You can do this. I know that sometimes you have glasses and you have ping pong balls. So this is something you can show your friends and they'll be impressed by it. If I blow air over the top of this, that creates what type of pressure? A high or a low pressure on top of it?
Low pressure.
I get a low pressure right here, but inside the glass, is it going to be high or low? It's going to be relatively high. So I create a low pressure just like with the hair dryer, but I have a high pressure inside of the glass. You ready? You want to watch? What's going to happen? It's going to fly out. Now, you might think, oh, the air just goes in and scoops it out. But that's not what's happening. That I'm actually creating a low pressure on top of the glass, and the high pressure air that's inside the glass shoots it out. This one's a little trickier. This is just a can. You know where they make these? Huh? No, it says that they're bottled in mini soda. Well, this is harder to do. Let's see if I can do it. Similar idea. If I put a high velocity stream across the top, I'll have a high velocity, low pressure streams. Then I'll get a high pressure down here, low pressure up here. That's a little hard though, because it's a little heavier than the ping pong ball, and it needs a higher speed. Listen, where does this come up? Y'all are a lot of your healthcare people. Where do you use this? No, not blood pressure. Anybody do respiratory therapy or something similar to that? The little machine thing, right. So, in respiratory therapists will often use a thing, I don't know what it's called, but they'll have, their patient here, and their patient puts a tube in their mouth. There's a cup that has liquid in it, and then there's a pipe that runs over it, and the air comes through and eventually goes to the person's mouth. What this does is it pulls the medicine up out of this cup and goes off to the person that's using it. It's called entrainment. It's not a CPAP machine, though. Although yes, a CPAP machine will add humidity to your air, and I think they do it through that method, but I'm not sure. Okay? Oh, shoot, we're almost done, aren't we? Well, let's do this quick test, then we'll do these 2 questions, then we'll wrap it up, okay? This shows a pipe, and they have stand pipes on top of the pipe. They use stand pipes on pipes to help you tell the pressure. So where is the pressure greatest? At point A, point B, or point C? In the stand pipe, which is open to the air, it's highest here, next highest, and lowest at C. Where is the pressure greatest, or is the pressure all the same? The water pressure, or the pressure of the fluid. Does anybody like lukewarm club soda? All right, we'll stop at 1 minute. 1 minute. And then we'll go on to the next one. So go ahead and look at that one and be thinking about it, and then we'll stop there. The next one's a little trickier. All right, the one with the highest pressure is A. Remember pressure, rho GH? So whatever has the highest column will have the highest pressure. It's just like with our blood pressure measurements, rho GH. So our highest pressure is right here at column A. Now, I want you to think about which of these statements describes the shape of the bottom portion of the pipe. Let me tell you, the pipe is not constant cross-section, so C is not the right answer. It's either going to narrow from left to right, that means it's going to go like this, or it's going to get wider from narrow to right, that means it's going to go like this, the pipe. So which of those is it? Is it A or B? Is the pipe going to narrow from left to right? Remember it had high pressure over to the left. Or is it going to get wider from left to right? Like that. Oh shoot, we're out of time, aren't we? I'll run it next time, but y'all think about it, and we'll pick up with this question, okay?